Lowell, Massachusetts, 1890. Inside the boot cotton mills, a single cast iron flywheel turns at 120 revolutions per minute. It is 25 feet across. 40 tons of solid iron spinning on a forged steel shaft the thickness of a man's torso. Connected to that wheel by leather belts running up to overhead line shafts are 700 power looms. Every shuttle, every heddle, every picking stick on every one of those machines draws its motion from this one wheel. If it stops, 800 workers stop with it. 800 families lose a day's pay. And the investors sitting in their offices on State Street in Boston lose money they are not willing to lose. That flywheel did not build itself. Somebody had to imagine it first. Then somebody had to pour molten iron at 2,600 degrees Fahrenheit into a mold the size of a small building. Then somebody had to wait, not hours but weeks, for it to cool without cracking. And then somebody had to move 100 tons of cast iron across the state of Massachusetts, lower it into a mill basement on timber skids, mount it on a shaft, and spin it up to operating speed without killing anyone in the process. Most of those somebodies have no names anymore. No headstones, no pension records. They built the thing that built American industry, and the country forgot them before the century was out. This is the story of the cast iron flywheel, the single most important machine component in 19th century America that almost nobody alive today has ever heard of. How they were made, who made them, what they cost in iron, in dollars, and in human life. And why, if you have ever worn a cotton shirt or lived in a house with milled lumber, you owe a debt to a spinning disc of iron and the men who kept it turning. If stories like this matter to you, the kind that remember what everyone else has forgotten, subscribe to this channel. We are not done with the forgetting. To understand why the flywheel mattered, you have to understand the problem it solved. And that problem was steam. By the 1820s, American manufacturers had figured out that steam engines could replace water wheels. You did not need to build your factory on a riverbank anymore. You could put it anywhere you had coal and water. But steam engines had a flaw that nearly killed the entire experiment before it started. A steam engine does not produce smooth, continuous power. It produces pulses. Every time the piston reaches the end of its stroke, there is a momentary dead spot where the engine produces almost no force at all. Then the piston reverses, pressure builds again, and another pulse of energy comes through. If you have ever watched a single-cylinder engine running on a test stand, you have seen it. The shaft speeds up, slows down, speeds up, slows down. Every single revolution. For pumping water out of a mine, that does not matter much. The pump just surges and pauses. But for driving a textile loom, it is fatal. A loom requires constant, steady rotation. The shuttle has to cross the warp threads at exactly the same speed every time. If the power surges, the thread snaps. If the power drops, the weave loosens. You get ruined cloth. Hundreds of yards of it, in minutes. Therefore, the question facing every mill owner in America in 1820 was not whether steam could provide enough power. It could. The question was whether steam could provide steady power. Smooth, relentless, unchanging rotational energy, minute after minute, hour after hour, for 12 or 14 hours a day, 6 days a week. The answer was no, not by itself. But there was a solution, and it had been understood in principle since the medieval period, though nobody had ever attempted it at this scale. You take a very heavy disc, you mount it on the engine's output shaft, and you spin it up. The mass of the disc stores kinetic energy during the power stroke. Then, during the dead spot between strokes, the disc's momentum carries the shaft through. The heavier the disc, the smoother the output. The faster it spins, the more energy it stores. The concept is elegant. The execution, in 1823, was anything but, because the disc had to be enormous. We are not talking about a 20-pound wheel bolted to a bench grinder. We are talking about a solid casting of gray iron, 25 to 30 feet in diameter, with a rim cross-section as thick as a man's chest. The largest mill flywheels weighed over 100 tons. They spun at 100 to 150 revolutions per minute, and the rim speed at the outer edge exceeded 60 miles per hour. If a flywheel of that size fractured while running, the fragments could tear through a brick wall like grape shot through paper. There was no safety cage large enough to contain it. There was no emergency brake fast enough to stop it. You either cast it right, or people died. That was the engineering problem of the age. And to understand who solved it, you have to go back a few years, to a man named Francis Cabot Lowell. Francis Cabot Lowell was born in 1775 in Newburyport, Massachusetts. He came from money. His family were merchants, Harvard men, the kind of New England aristocrats who expected their sons to enter trade or law. Lowell did enter trade. He became a successful import merchant. But on a trip to England in 1810, he saw something that changed the direction of his life and, ultimately, the direction of American manufacturing. He toured the textile mills of Lancashire. He watched the power looms. He studied how raw cotton went in one end of a building and finished cloth came out the other. The English called it the integrated mill, and they guarded the technology fiercely. It was illegal to export the plans. It was illegal to export the machinery. It was illegal for a trained textile mechanic to leave the country. Lowell memorized what he saw. Not sketches, not stolen blueprints. He watched the machines work, studied the gearing, traced the power transmission from the water wheel through the line shafts to the looms, and he committed it to memory. Then he sailed home to Boston in 1812, while the War of 1812 raged on the Atlantic, and spent the next 2 years in a workshop with a brilliant mechanic named Paul Moody, reconstructing the English power loom entirely from what he carried in his head. By 1814, they had a working prototype. By 1823, the Boston Manufacturing Company had built the first integrated textile mill in America, on the Merrimack River in a town that would eventually bear Lowell's name. Francis Cabot Lowell himself did not live to see it completed. He died in 1817 at the age of 42 from exhaustion and illness. The men who carried his vision forward named the city after him. But the problem he identified before he died, the problem of steady power, would define the next 70 years of American manufacturing. Here is what most histories leave out. Lowell did not just need looms. He needed the looms to run at constant speed, every hour, every day. A cotton thread under tension does not tolerate variation. It does not forgive a surge of power any more than it forgives a drop. He needed flywheels, enormous ones. And in 1823, nobody in America had ever cast one that large. The knowledge existed in England. The foundries existed in England. But Lowell's partners had to find someone on this side of the Atlantic willing to attempt it, knowing that a failed casting meant weeks of wasted labor and tons of wasted iron. The foundries that took on this work were not clean, well-lit facilities. They were dark, roaring caverns of heat and noise. The largest was the Hinckley Locomotive Works in Boston, founded by a man named Holmes Hinckley. Hinckley had started as a machinist, built his reputation on precision steam engine components, and by the 1840s, his foundry was casting some of the largest single-piece iron objects in the Western Hemisphere. The process of casting a flywheel began weeks before any iron was melted. First, the pattern makers built a full-size wooden model of the wheel. For a 25-foot flywheel, that model filled an entire room. It had to be precise to within a fraction of an inch, because every flaw in the pattern would be reproduced in iron. The pattern was then pressed into specially prepared molding sand, a mixture of sand, clay, and water, packed into a casting pit dug into the foundry floor. The pit for a large flywheel might be 30 feet across and 6 feet deep. The mold was built in sections, with channels and vents carved to allow the molten iron to flow in and the gases to escape. Then came the pour. A blast furnace, charged with pig iron, coke, and limestone, was brought up to temperature, 2,600 degrees Fahrenheit. At that heat, iron does not glow red, it glows white. The air above the crucible shimmers. The foundry floor radiates heat that you can feel through the soles of your boots from 30 feet away. The men who worked the pour wore heavy leather aprons, leather gloves to the elbow, and leather hoods to protect their faces. There was no ventilation system worth the name. The smoke and fumes pooled at the ceiling and drifted down. Carbon monoxide, sulfur dioxide, iron dust. You breathed it until your shift ended, or until you could not breathe anymore. For a 100-ton flywheel, the pour took between 4 and 10 hours of continuous work. Multiple furnaces feeding multiple ladles, each ladle carried by teams of men using long iron rods because the heat would burn through any rope. The iron had to flow into the mold at a steady rate. Too fast, and the mold could rupture from hydrostatic pressure, sending a river of white-hot iron across the foundry floor. Too slow, and the iron already in the mold would begin to solidify before the pour was complete, creating a cold shut, an internal seam of weakness that might hold for years or might let go the first time the wheel hit full speed. Every man in that foundry knew what a cold shut meant. They had all seen a fractured flywheel, or they knew someone who had. After the pour, the waiting began. A large casting could not be removed from its mold for 2 to 4 weeks. The cooling had to be gradual. Too fast, and thermal stress would crack the wheel before it ever turned. So the mold sat in its pit, covered with sand, and the foundry worked around it. Men walked past it every day on their way to other pours, other castings. Somewhere under the sand, 100 tons of iron was slowly, silently contracting, and nobody knew whether it had cracked until they dug it out. When the mold was finally broken open, the wheel was inspected by eye and by hammer. A man would walk the rim and strike it with a steel hammer every few inches, listening to the ring. A solid casting produces a clear, bell-like tone. A cracked casting produces a dull thud. If the ring was wrong, weeks of work and tons of iron were scrap. There was no way to weld a flywheel, no way to patch it. You started over. The ones that passed inspection were machined on lathes so large they were bolted to granite foundations sunk into bedrock. The bearing surfaces had to be true to thousandths of an inch. Any imbalance in a wheel, spinning at 150 revolutions per minute, would shake the entire mill building. Then the finished wheel was loaded onto a reinforced freight wagon, or later a railroad flat car, and transported to its mill. And this is where men like Kirk Boot enter the story. Kirk Boot was not a gentle man. He was a former officer in the British Army, trained at the Royal Military Academy at Woolwich, and he brought a military precision to everything he touched. He had served in the Peninsular War. He had seen men die under orders he had given. And when the Boston Associates hired him in 1821 to oversee the construction of the entire Lowell mill complex, he applied the same expectations to bricklayers and carpenters that he had once applied to soldiers. The work would be done correctly. It would be done on schedule. He did not tolerate excuses, and he did not tolerate sloppy craftsmanship. Boot designed the layout of the original Boot cotton mills, the buildings that still stand today along the Merrimack Canal. He chose the proportions, he specified the brick, and he personally supervised the installation of the first central flywheels, which was itself a feat of coordination that would challenge a modern crane operator, let alone a crew working with block and tackle and timber cribbing. Consider the geometry. You have a cast iron wheel, 25 feet in diameter. It weighs somewhere between 40 and 100 tons, depending on the specific casting. You need to lower it into the basement of a brick building through an opening in the floor that was built specifically for this purpose, onto a forged steel shaft that is already mounted in its bearings. The shaft has to be level to within fractions of an inch. The wheel has to be centered on the shaft to within the same tolerance. If the wheel is even slightly off-center, the vibration at operating speed will shake the bearings apart within months. Boot understood this. He stood in the basement and watched every inch of the lowering, and the men on the ropes knew that if they dropped it, there would be no second chance and no forgiveness. Each mill building at Lowell was designed around its flywheel. The wheel sat in the basement, mounted on a forged shaft that ran the width of the building. From that shaft, leather belts ran upward through slots in the floor to overhead line shafts on every level. From the line shafts, smaller belts ran down to each individual loom. The entire system, from the flywheel in the basement to the shuttle on the top floor, was one continuous chain of mechanical power transfer. Every belt had to be tensioned correctly. Every shaft had to be aligned. Every bearing had to be greased on schedule, by hand, by a man or a woman reaching into a mechanism that was still moving. If you have ever stood in a working mill and listened to the sound, you know it is not something you forget. The flywheel produces a low, continuous hum that you feel in your chest more than you hear with your ears. The line shafts add a higher whine. The belts slap against their pulleys with a rhythmic cadence, and above it all, the clatter of the looms, hundreds of them, slamming their shuttles back and forth 12 times a second. The noise was so intense that mill workers developed their own system of lip reading and hand signals, because spoken conversation was impossible. I have stood inside the Boot Cotton Mills Museum in Lowell, where they still run a bank of original power looms connected to a line shaft for demonstration. You can still hear the line shaft when they run a demonstration. Even with only a fraction of the original machines running, the noise is staggering. You feel it in your teeth, in your rib cage. The wooden floor vibrates. The air itself seems to thicken with the sound, and you realize that men and women worked in that sound for 12 hours a day, 6 days a week, for years. Not because they loved it, because it was work, and work was survival. But the flywheel's reach extended far beyond textiles. By the 1850s, the same technology was driving the sawmills of the Pacific Northwest. The timber industry needed something that could spin a circular saw blade 7 feet across through a Douglas fir log 4 feet in diameter. The forces involved were enormous. A 7-foot saw blade spinning at the correct cutting speed has a rim velocity that approaches 140 miles per hour. The teeth are hardened steel, each one filed by hand to a precise angle, and when they bite into green Douglas fir, the resistance is tremendous. If the blade binds in the cut, if the log shifts or the grain twists, the shock load on the drive system is measured in tens of thousands of foot-pounds. That shock has to go somewhere. Without a flywheel, it goes straight back through the drive shaft to the engine, stalling the piston, snapping belts, cracking gears. With a flywheel, the stored kinetic energy absorbs the shock. The blade slows for a fraction of a second and then recovers. The engine never notices. The sawmill flywheel had to be tough in ways that a textile mill wheel did not. Textile mills ran at constant load all day. Sawmills ran at variable load, minute to minute, because every log was different. A clear-grained fir ran through the blade like butter. A knotted old-growth cedar could stop a blade cold if the flywheel did not have enough momentum to push through. Therefore, the sawmill wheels tended to be heavier for their size, with thicker rims and wider hubs, built to store more energy per revolution than a textile wheel of the same diameter. The sound of a sawmill flywheel was different from a textile flywheel. In a textile mill, the hum was constant, almost musical. In a sawmill, the hum rose and fell as the blade entered and exited the cut. You could hear the pitch change every time a log was fed. The mill workers who tended these machines could judge the quality of a log by the sound the flywheel made when the blade hit it. A clean tone meant clear wood. A grinding, stuttering tone meant knots or embedded metal, old nails or fence wire grown into the tree decades earlier, waiting to shatter a sawtooth and send a shard of steel across the mill floor. The foundries that served the timber industry were concentrated in Pittsburgh and in smaller operations along the Ohio River Valley. The Carnegie foundries, before Andrew Carnegie turned his attention entirely to steel, cast flywheels for sawmills across the country. The Phoenix Iron Works in Phoenixville, Pennsylvania, was another major supplier. These were not boutique operations. They were industrial facilities running multiple blast furnaces, employing hundreds of men, pouring iron around the clock. If you are still watching, if you have made it this far into a story about cast iron and forgotten foundry workers, then you are exactly the kind of person this channel exists for. Hit subscribe. There is more to remember. The men who operated these flywheels in the mills were called engineers, but the title carried a different weight than it does today. A mill engineer did not have a degree. He had experience. He had years of watching, listening, adjusting. He knew the sound his flywheel made when the bearings were properly greased, and the sound it made when they were running dry. He knew the vibration that meant a belt was slipping, and the vibration that meant a shaft was going out of alignment. He knew that a flywheel does not stop quickly, that even after the steam is cut, a 100-ton wheel carries enough momentum to keep spinning for 20 minutes or more. And he knew what happened when things went wrong. Flywheel failures in the 19th century were catastrophic events. When a wheel fractured at operating speed, the fragments did not fall, they flew. A section of rim weighing several tons, traveling at 60 miles per hour, would go through anything in its path. Brick walls, timber beams, iron columns. At a textile mill in Fall River, Massachusetts in 1874, a flywheel burst during normal operation and killed 3 workers instantly. The cause was determined to be a cold shut in the casting that had gone undetected for 7 years. The wheel had been running every working day for 7 years, with a hidden crack that grew a fraction of an inch at a time until the iron could no longer hold. There was no investigation in the modern sense, no regulatory agency to report to. The dead were buried. The wheel was scrapped. A new one was ordered. Production resumed within weeks. This was the pattern across the industry. At the Hinckley Works in Boston, foundry records from the 1850s mention lost time accidents in language that barely qualifies as record-keeping. A note in a foreman's ledger might read simply, "One man burned," or "Hand crushed, pouring floor." No names, no follow-up entries. The men were often immigrants, Irish and German in the eastern foundries, Scandinavian and Chinese in the western ones. They came because the work paid better than anything else available to a man without English or formal education. They stayed because they had no alternative. And some of them died because the economics of casting iron did not leave room for caution. I have walked through old foundry sites in Pennsylvania where the brick walls still stand, but the roofs are gone. The casting pits are filled in now, covered with dirt and weeds. There are no markers, no plaques. You would not know that men poured iron there unless you recognized the shape of the furnace foundations or the scoring on the remaining walls where ladle chains once ran. The iron is gone. The men are gone. The names were never recorded, but their work shaped the country. Every bolt of cotton cloth that came out of Lowell passed through a machine driven by a flywheel cast in a foundry like these. Every board cut in a Pacific Northwest sawmill was sliced by a blade kept spinning by a flywheel some foundry crew had poured and prayed would hold. The infrastructure of 19th century America, its buildings, its clothing, its ships, its railroads, ran on the momentum stored in cast iron discs that most Americans never saw and never thought about. The system worked. For decades, it worked. But it was never static. The demands on flywheels grew as mills grew. The Merrimack Manufacturing Company in Lowell, which had started with a single mill building and a single flywheel in the 1820s, was running multiple buildings with multiple wheels by the 1860s. Each building had its own engine and its own flywheel. Each flywheel drove its own system of line shafts and belts. The complexity was staggering. A maintenance map of the boot cotton mills in 1880 showed over 4 miles of leather belting in a single building. Every belt had a service life measured in months, not years. Every belt had to be inspected, spliced, or replaced while the system was running, because shutting down meant shutting down production, and shutting down production meant losing money. The belts themselves were made from cowhide, tanned and stitched into continuous loops. A main drive belt running from the flywheel to the primary line shaft might be 12 inches wide and over 60 feet long. It ran at speeds that would tear the skin off a man's hand if he touched it while it was moving. And it moved constantly. 6 days a week, 12 hours a day, from the moment the engine built up steam in the morning until the whistle blew at night. The belt tenders who maintained this system were among the most skilled and most endangered workers in the mill. They worked on ladders and catwalks between moving shafts, reaching into spaces where a loose sleeve or an untied apron string could catch on a belt and pull a person into the machinery in less than a second. A belt tender had to be able to judge by eye whether a belt was tracking true on its pulley. He had to be able to splice a broken belt in minutes, working in dim light with the line shaft still turning above his head. He carried a knife, a punch, a lacing tool, and a block of belt wax in a leather pouch at his waist, and he used all of them every day. Accounts from Lowell mill workers in the 1840s and 50s described the belt tenders as the bravest people in the building. Some of them were women. Some of them were children as young as 12. Therefore, when the electric motor arrived in the 1890s, it did not just replace the flywheel, it dismantled an entire world. An electric motor produces smooth, constant torque from the moment it starts. It does not need a flywheel to even out its power delivery. It does not need a system of belts and line shafts to distribute power through a building. You can put an electric motor on every machine. Each loom gets its own motor. Each saw gets its own motor. The overhead shafts come down. The belts are cut and thrown away. The flywheel, the center of everything, is suddenly unnecessary. Think about what that means from the perspective of a mill engineer who spent 20 years tending a flywheel. His entire skill set, the ability to read vibrations, to listen for bearing wear, to manage a mechanical power distribution system of almost unimaginable complexity, became obsolete in a single decade. The new electric mills did not need him. They needed electricians. They needed motor mechanics. They needed men who understood wire and insulation and circuit breakers, not men who understood iron and leather and the behavior of a spinning mass at 150 revolutions per minute. The transition happened faster than anyone expected. In 1890, virtually every factory in America ran on steam and flywheels. By 1900, electric motors were being installed in new construction across New England and the industrial Midwest. By 1910, existing mills were converting, ripping out their line shafts and installing individual motor drives. By 1920, the flywheel era was over. 30 years to erase a technology that had defined American manufacturing for nearly a century. 30 years to make obsolete a skill that had taken generations to develop. The flywheels themselves were too large to move easily, and too heavy to be worth the cost of scrapping for most mill owners. Many were simply left in place, abandoned in basements that the new electric mills no longer needed to access. They sat in the dark. The grease on their bearings dried and hardened. Dust settled on the rims. Spiders built webs in the spokes. The iron that had once hummed with stored energy went cold and still. When the old mills were eventually demolished, the wheels went to the scrapyard with everything else. Melted down, returned to the furnace. The iron in a flywheel that powered Lowell's looms in 1850 might be part of a bridge girder, or an engine block, or a manhole cover today. There is no way to know. The iron carries no memory of what it was. But some survived. At the Boot Cotton Mills Museum in Lowell, Massachusetts, original flywheels are still in place. You can stand next to them. You can put your hand on the rim and feel the surface that foundry workers smoothed on a lathe 160 years ago. The iron is cold now. It does not turn. But the scale of it still registers in your body. 25 feet across. The rim at eye level is as wide as your shoulders. And when they run the demonstration, when they start the line shaft and the belts begin to move and the looms begin to clatter, you can hear something underneath all of it, a low hum, the residual vibration of a system designed to never stop. I have stood there and listened to it, and I have thought about the men who poured that wheel, the foreman who struck it with a hammer and listened for the ring, the engineer who spent 30 years in the basement with it, greasing the bearings, tightening the shaft bolts, listening for any change in the sound that meant trouble was coming. None of their names are on the wall. None of their photographs are in the exhibit. The museum tells the story of the mill girls, which is important and deserves to be told. It tells the story of the investors and the engineers, which is part of the record. But the foundry workers, who made the thing that made everything else possible, are represented by their absence. They are the space between the displays. I want to tell you something about what it means to forget. A cast iron flywheel is a permanent object. The iron does not decay. It does not rot. Left in place, protected from weather, a flywheel could last 1,000 years. The men who made it were temporary. They lived 30, 40, 50 years if they were lucky. They breathed iron dust and furnace smoke, and they carried burns on their arms. And they went home at night to tenement rooms in neighborhoods that no longer exist. They were not temporary because they chose to be. They were temporary because nobody thought to write their names down. And this is the fundamental asymmetry of the industrial age. The machines endure. The workers do not. The objects we can still touch, still see, still stand next to in a museum, were made by people we can no longer name. The flywheel is a monument to its own makers, but it is an anonymous monument. It says, someone was here. It does not say who. If you have watched this far, I want to ask you something directly. Subscribe to this channel. Not because of algorithms or metrics, but because these are stories that will disappear if nobody tells them. The last generation that worked near line shafts and flywheels is gone. The grandchildren who might have heard the stories are growing old now too. This is the window. It is closing. Help us keep it open. There is a foundry in Phoenixville, Pennsylvania, the Phoenix Iron Works. It operated from 1827 to 1987. In its prime, it cast flywheels and bridge components and cannon barrels and anything else that required large quantities of iron poured with precision. The main building still stands, converted now into a community space. The furnace foundations are still visible if you know where to look. The walls still bear the marks of a century and a half of industrial work. When I visited, it was a Tuesday afternoon. The building was quiet. A few people were eating lunch in what used to be the molding floor. I stood where the casting pit would have been, where crews of men once poured iron that would keep mills running in 3 states, and I thought about how strange it is that the most consequential work in a nation's history can be done in a place that the nation will eventually turn into a restaurant. We do this with all of our industrial heritage. We eat lunch where men burned. We hang art where women lost fingers. We call it adaptive reuse, and we congratulate ourselves on preserving the building while erasing everything that happened inside it. But the iron remembers. If you go to Lowell and put your hand on that flywheel, You are touching something that last felt human hands when Grover Cleveland was president. The marks on the rim are tool marks from the machining. The slight discoloration near the hub is where grease accumulated over decades of operation. These are not artifacts in the usual sense. They are evidence. Evidence that someone stood here. Someone worked here. Someone made this with their hands and their backs and their knowledge of how iron behaves when it cools. The cast iron flywheel did not invent American industry. It did not build the railroads or win the wars or settle the frontier. But it made all of those things possible by solving a problem so fundamental that we have forgotten the problem even existed. How do you turn the irregular, pulsing energy of a steam engine into the smooth, constant power that machines require? You pour 100 tons of iron into a disc and you spin it. And then you trust it. For nearly a century, that trust was the foundation of American manufacturing. Every loom in Lowell, every saw in the Pacific Northwest, every lathe and drill press and grinding wheel in every machine shop from Boston to San Francisco drew its power from a flywheel turning in a basement or a back room. The wheels were there when Francis Cabot Lowell built his first integrated mill. They were there when Kirk Boot drove his workers to exhaustion to meet production schedules. They were there when Holmes Hinckley's foundry crews poured iron in the summer heat of a Boston foundry with no ventilation and no protection. They were there through all of it, turning, storing energy, releasing it, keeping the machines steady, keeping the production running, keeping the country moving. And when the electric motor came and the wheels finally stopped, nobody held a ceremony. Nobody said thank you. The belts were cut. The shafts were disengaged. The great iron discs, 25 feet across, 100 tons, spun down for the last time and went silent. The mills kept running on a new kind of power. The foundries moved on to new products. And the flywheel, the machine that had made the age possible, became scrap metal and museum exhibits and footnotes in engineering textbooks that almost nobody reads. I think about the last engineer who tended the last steam-driven flywheel in a Lowell textile mill. Sometime around 1915, maybe 1920, a man who had spent his career in a basement, listening to the hum of a wheel his grandfather's generation had cast. He would have known the sound better than his own heartbeat. He would have known every bearing, every belt connection, every vibration pattern. And one day, someone told him the mill was converting to electric. The wheel would stop, his job would change, or his job would end. I wonder if he stood there for a moment after the steam was cut, watching the wheel slow, feeling the vibration fade from the floor under his feet, listening to the hum drop in pitch as the revolutions fell away, from 120 to 100 to 80 to 60 to a slow, ponderous turning that you could count, one revolution at a time, until it stopped. That would have been the last sound of the flywheel era. Not a crash, not an explosion, just a fading hum, lower and lower until it was gone, and then silence. The wheels are mostly scrap now, but the ones that survive are still there, in Lowell and in a few other places where someone decided that the iron was worth keeping. You can visit them. You can touch them. You can stand in the space where a spinning disc of iron once kept 800 people employed and an entire industry running. And if you listen carefully, in the silence of a museum built inside a mill that used to shake with the noise of 700 looms, you can almost hear it. That low hum. The sound of a wheel that someone poured, and someone mounted, and someone tended, and someone trusted every day for the better part of a century. They deserve to be remembered. This is how we remember them.